The car you see right here isn't just another car from Toyota, and it's not just another hot hatch with weak power output covered up by good handling characteristics. This car, as you probably already know, is the Toyota Yaris GR, and it's a big middle finger to pretty much all hot hatches ever made. What makes it special compared to everything else is the fact that it's a homologation car, which isn't something Toyota has really done in about 20 to 30 years, and it's not something that's really done at all anymore by anyone. If you look at Toyota's track records for their sports cars and their performance cars, the more recent records aren't so good looking for Toyota. You have the BRZ GT86 FRS, which is a great car, but the motor comes from Subaru, so it's really not a Toyota product. And then you have the Supra, another really great product, but at the end of the day, it's mostly BMW, which isn't a bad thing, but it's still not Toyota. This is where the Yaris GR is different in the fact that it is Toyota through and through. It is designed by them, it is built by them, it's a full Toyota product. The Yaris GR has a ton of cool features, and it's a really cool car, but at the end of the day, we're here for the motor. And that motor is the G16E-GTS. It's a 1.6 three-cylinder motor that makes a ton of power and has a ton of cool features. Really, it's unlike anything we've seen before on this channel or in general when it comes to performance engines, and it's arguably the best three-cylinder ever made. So sit back, relax, grab your popcorn, let's sit down and dissect the Toyota G16E-GTS. As you probably know, Toyota really hasn't been making much of anything in terms of performance engines in the last decade or two. Really, they peaked out around the 2JZ, and it's been a slow decline ever since. Now, that's not to say that they don't make any performance engines, because you have things like the 3S GTE. It's just that they haven't really made anything particularly special or interesting during that time. At the end of the day, it makes sense. Toyota's going to make a lot more money building really cheap, reliable, and eco-friendly kind of little cars like the Corolla or the Camry or the Avalon, you know, something that's just for the everyday person. There's really not that much money in the performance car market, which just makes the Yaris GR and the G16E-GTS even more special because it's just totally abnormal for Toyota at this point. Of course, the sentiment that Toyota hasn't really made anything good in terms of their performance engines was really flipped on its head with the G16E-GTS. A small 1.6 three-cylinder unlike anything Toyota has ever built for their production cars. Something that is worth noting before we get too deep into this video is that this engine has to comply with Euro 6 emission standards, which means that Toyota has to make a lot of changes and design choices in the name of improving efficiency. You'll see this throughout the video as we dissect the engine. Taking a closer look at this engine, let's look at it from the top down, starting with the cylinder head. Starting with the most basic set of information, the G16E-GTS is a dual overhead cam 4-valve per cylinder engine. Since it only has 3 cylinders, this brings the total valve count to 12, which is a little weird seeing the 12 number attached to the valve count if you're used to something like a 4-cylinder engine, which almost always has 16 valves, but that's a little bit off topic. The head itself is constructed from cast aluminum, just like pretty much any modern head, and what's actually interesting is inside that casting there's a 2-level cooling system. So there's 2 levels to the cooling jackets. Now, this was done for thermal efficiency and ultimately total engine efficiency, and it's not something you really see when it comes to cylinder heads. Of course, cooling had to be a very big focus for this engine. At the end of the day, it's going to be used in a lot of track cars and track type of situations. It's going in the Yaris GR, it's going to be used on track, and it's going to be used for extended periods of time. So the cooling needs to be exceptionally well designed and balanced. Rather than variable valve lift, Toyota opted to give this engine variable valve timing through the use of cam phasers on the front of the camshafts, which by the way are hollow to save weight and reduce parasitic loss, ultimately helping to improve efficiency even further. On the intake cam, the system gives the G16E-GTS 70 degrees of camshaft timing adjustment, and on the exhaust side it has 41 degrees of camshaft timing adjustment. Now you might be wondering why the intake side has more adjustment, and that's because the intake side uses VVTi-W and the exhaust side only uses VVTi. It's also worth noting that you'll generally see more performance and efficiency benefits from having larger adjustment ranges on the intake side as compared to the exhaust side. Taking a closer look at the ports on the engines, you'll notice something very different from most engines, and that is the design shape and angle of the port. To put it really simply, the ports on the G16E, like for example the intake and exhaust port, they're much more angled. Going from the, basically the face of the port all the way down to the cylinder, they're way more angled, whereas like a Honda engine, they're going to be very, very flat. Now, this was done for a handful of reasons, but most of this revolves around the increased valve angle on this motor. By using a steep intake port and an increased valve angle, the air flows over the backside of the valve into the cylinder rather than going around the backside of the valve. So it's going over it instead of around it. When you visualize this, you'll see that the result is a much better path for intake flow, which ultimately results in better flow, fuel atomization, and ultimately more efficiency and power. The exhaust valves are filled with sodium for improved cooling, which is something you'll find on the significant portion of performance-oriented engines. Where things get even more interesting with the ports is that Toyota uses CNC machines to partially smooth out the intake ports. When the head is made, it has a rough finish because it's a cast material, so it's a little bit porous. A process which used to be more popular, known as porting and polishing, is a process where the ports would be enlarged and smoothed out. The smoothing out is done to help improve airflow by letting the air flow more smoothly into the cylinders, at least in theory. On the G16E-GTS, Toyota isn't hand polishing the ports, but they are using CNC machines to smooth out the entrance of the intake ports while leaving the rest of it rough. In theory, this should help improve performance and efficiency. It's just very odd that Toyota is only smoothing out the front part of the intake ports and not the back part where it meets the valves. Now, this could be done just to help improve the transition between the intake manifold and the intake port, but that's just speculation on my part. The intake manifold itself uses a variable runner length system, which you'll see on a lot of other Toyota engines. Now, this system basically works by having a flap inside the intake manifold which can either lengthen or shorten the intake runner. Now, this works by either, like if you were to close the valve, the path from the intake manifold would be very straight. The intake runner would be very straight and very short, whereas if you were to open the valve, it's going to be routed in a different direction, typically in a big loop. So it's going to effectively lengthen the intake runner. The length of the intake runner has a big impact on airflow velocity as well as power. So in certain circumstances, for example, low RPMs, a different intake manifold length is going to provide you with more power as compared to high RPM. Now, in terms of injection, the G16E-GTS isn't anything particularly special because it just uses Toyota's D4S fuel injection system like all other dynamic force engines from Toyota, which consists of both direct and port injection for the best of both worlds. To put that simply, direct injection offers a lot more accuracy and precision regarding fuel spray and timing, while port injection helps to minimize carbon buildup on the valves, and port injection is also much easier to upgrade for aftermarket performance compared to direct injection. Now, on the turbocharger, it's again kind of surprising to see such a simple setup. Like you'll find on many modern cars, the turbo is integrated with the exhaust manifold as one large unit. This is something you'll see on other Toyota engines like the 3S GTE, but also on performance engines like the BMW N55. The turbocharger itself is a relatively small unit to help give the engine really great low-end power and throttle response, but it's not excessively small like Ford EcoBoost Turbo, for example. It features a ball bearing setup and it uses a single scroll design. Now, you might be wondering why it doesn't use a twin scroll like you'll see on other modern performance engines, and that's because there's effectively no benefit to a twin scroll when the engine that is bolted to only has one bank. Now, what I mean by this is that this engine is only a 3-cylinder, meaning it effectively only has one bank of cylinders. Now, a twin scroll really only benefits if there are two banks. So you have two scrolls, and for example, on an inline 6, you'd have 3 cylinders powering each scroll of the turbocharger. In this case, there's only 3 cylinders in the first place, so there would be no benefit to splitting. You would have 1.5 cylinders, if you do the math, right? 3 divided by 2, you'd have 1.5 cylinders per scroll. It makes no sense, so a single scroll was used on this engine. Moving down from the cylinder head, let's take a closer look at the cylinder block and the internals inside the engine. Just like the head, the block is constructed of cast aluminum, which again is pretty standard across all modern engines. It's basically done for weight savings and thermal efficiency, and because there's really no good reason to use cast iron in this type of application, unless the potential reduced manufacturing costs are an absolute priority, which in this case, it's really not. The block uses an open deck design, which did surprise me a little considering how performance oriented this engine is. We've covered this in detail in other videos, but basically a closed deck design provides much better cylinder stability, especially at the top of the cylinder where in-cylinder pressure gets the highest. The open deck design improves cooling and reduces hot spots in the cylinder, but provides much less strength and rigidity at the top of the cylinder. Considering how high cylinder pressure is on this engine, you'd think that Toyota would use the closed deck design, but they just didn't. The sleeves for the cylinder are made from cast iron and they're super thin to the point that you can't even bore this engine out. If there was terminal failure somewhere in the engine and the cylinder needed to be bored out as part of the rebuild process, you would literally just have to buy a new block instead. The pistons are constructed from aluminum and use a T-shaped design, Another thing which surprised me during the research for this video is how high the compression ratio is on this engine at 10.5 to 1. That used to be pretty high for a naturally aspirated engine, so seeing this in an application with upwards of 20 to 30, even 40 pounds of boost in aftermarket performance settings, that's a very high compression ratio. The Pistons also feature thin inner walls for reduced weight on the rotating assembly, which again just improves efficiency even further. The connecting rods are forged steel, as you'd expect from a small performance engine, and the crankshaft is also forged steel, again, as you'd expect from a small performance engine. Now, where this engine gets very interesting in terms of the rotating assembly is that Toyota offset the crankshaft 10 degrees from the center line of the cylinder. So what I mean by that is that you have the cylinder right here, and normally you'd have the crankshaft directly underneath it. 1-to-1, perfect. This motor, it's offset, so you have the crankshaft away 10 degrees relative to the cylinders. Now, this was done to reduce the piston to cylinder wall friction and improve efficiency even further. It's just very strange to see this on a performance engine, and it's not something I've really seen on many other engines. So I'm curious to see if Toyota is going to be doing this moving forward with all of their performance engines, or if other manufacturers will also pick up on this. The crank throw of this engine is 120 degrees, which is typical for a 3-cylinder engine, so nothing really special in that regard. Because of the inherently unbalanced nature of engines with odd numbers of cylinders, Toyota did add in balancing shafts to help reduce vibrations felt in the cab. This engine features a total of 9 piston oil squirters, that's 3 per cylinder. Now, there are some people that would argue that you really don't need piston oil squirters and blah, 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 blah. But at the end of the day, this is an engine that is designed for high load use, so track use, where you're at full throttle, full boost for extended periods of times. And we're talking about a small 3-cylinder engine. So you have a lot of boost, that's more heat, only 3 cylinders. So all that heat has to be absorbed by just 3 cylinders, not like 4 or 8, for example. So you have a ton of heat, a ton of pressure in each cylinder. Those pistons are going to melt in any other application if you did not have piston oil squirters. If you're at full boost, full throttle for minutes on end, your pistons will literally melt in other applications, or in this case, it would melt in this application if it did not have piston oil squirters. That's why there's 3 of them per cylinder, because this engine is designed for that prolonged high load use. The last thing worth noting on the block and bottom end is that there's a massive girdle which holds everything together. The block is essentially a rigid 3-piece design with one main bearing girdle holding the entire bottom end together rather than individual main caps. Ultimately, this is just a way stronger and way better design overall, but it does increase manufacturing costs. Now, a couple of things I did not mention in this video, which I think are worth mentioning, is the fact that this engine is Toyota's most powerful engine ever in terms of power per liter at 167.5 horsepower per liter. The previous record for Toyota was held by the 3S GTE, and as far as horsepower per liter for turbocharged production engines, this engine is actually pretty high up there in terms of power per liter relative to any engine from any manufacturer in any production car. Another thing worth noting is that the bore is 87.5 millimeters and the stroke is 89.7 millimeters, which is a surprisingly long stroke for a performance application. I suspect Toyota did this to help basically improve the power band, so you don't want a ton of top end power and you don't want just a ton of low end power. So you combine the moderately sized turbocharger with things like the increased valve angle and the variable valve timing, you end up with an engine that can produce a lot of power basically across the entire rev range. So it's not really dominant on the low end like a Ford EcoBoost would be, and it's not really dominant like on the high end like a big turbo 2JZ would be. It's really well balanced, which means a better driving experience and power all across the rev range. Overall, this engine is pretty awesome. I think it's fantastic. It has a lot of cool features that we went over in this video. It makes a ton of power. It's really small. It sounds really cool. And it's just basically one of the best products that Toyota has made in the last 10, 20, even 30 years. If you guys think I missed anything or there's anything you want to add to this conversation, drop a comment down below. While you're down there, smash the thumbs up button, get subscribed so you don't miss out on our future videos. Check out all the other videos on the channel. We go over engine basics, specific engines, compare engines, and a whole bunch of other stuff. And I'll see you guys in the next video.